is about using co-folding model and free energy method trying to solve the target deconvolution problem. So, okay, yeah. A lot of people have been talking about FEP and, this type of method is used widely in the industry. It has good accuracy when it works. It has some critical issues as well, where you need some structure to begin with. And it is expensive and slow. So, it's kind of usually used in the late stage of discovery. And in the early stage, then people kind of prefer to use machine learning methods because it's ligand-based and it is cheap and fast. So the question is that, can we expand the domain of applicability? So yeah, this is kind of how traditional drug discovery company do things. You have the target ID, you identify the target, and then you go to the hit ID stage where you try to screen a large library of compound. So it seems in this case, it's very often you don't have structures and you need to screen a large library. So you don't really use free energy method a lot. And then you go to hit to lead. In this case, if you have crystal structure, then you can sometimes use ABFE because your ligands are not conjugate series. And when you go to the lead optimization, then this is kind of the main application area where you have conjugate series and you have structures, you have everything. So recursion recognized that this kind of traditional drug discovery pipeline is good if your target is good, but if your target is bad, then all the downstream process are just waste of time. So yeah, recursion had this brilliant idea where it tries to, in the hit ID stage, it's instead of trying to screen a lot of compound against a single target, it tries to screen a large library against the entire genome. So the way recursion does that is that it does some cellular assay at this stage, and then I try to screen for the compound, which gives you the desirable phenotype. Well, obviously, you can't really do the lead optimization with the internal genome on phenotype. So you still need to go from the entire genome to a single target. And this is called target deconvolution in recursion. And the aim of target deconvolution is that you have a couple of hits which give you the desirable phenotype. And you want to screen the whole genome, or at least the whole kinome, and trying to find the target which binds your hits. So you try to see if it is a binder or a non-binder. Cool. So it was not possible in the past, but given now that there is this rapid advance in the co-folding structure, there's hope that this is something which could be done now. AlphaFold 3 claim that they can give you a highly accurate protein ligand structure. So it gives you the structure, it gives you the right pose. And in theory, you should just be able to run ABFE from that. And we choose the ABFE as our main binding free energy method because it allows you to handle any ligand. And also it kind of fits nicely with the recursion vision where we try to make everything industrialized. So we want to have a pipeline where protein sequence in and smiles in, and you got a delta G binding going out from the other side. And running this pipeline will help us solve another problem which we have is trying to keep the GPUs in our local supercomputing cluster hot. Good. So yeah, this is the proposed solution. You use the open source version of the co-folding model, trying to prepare your protein ligand complex. And then you try to find a pipeline which try to hook your ABFE calculation up with the Boltzmann output. And by doing this, we can just, no need for experimental crystal structure anymore, and you can run any free energy calculations at any time you want. So as usual, the advertisement does not really represent the real world situation. So when we are trying the co-folding model, we had a bunch of issues. Co-folding model does not understand chemistry, so it gives you the wrong ligand out, and you can have clash, and you can have a long region which is just cracked in your protein structure, and biology can sometimes be quite important as well. So we will go through this one by one. So yeah, if you want to do free energy calculation, then it is very important that you need to get your ligands correct. And this is something which the co-folding model, or at least Bose-1, does not do very well in. And you ask Bose-1 to give you a cyanide, it gives you an amine. You ask it to give the right stereochemistry and give you the wrong stereochemistry. And you ask it to give you a cyclohexane and it gives you benzene back. And this is obviously bad. So the way that we try to solve this problem is, using the traditional docking. So we have examined with two docking methods, the posit and the hybrid. So posit kind of is the kind of the choice which we made, and it starts with an MCS overlay. And then it tries to fit the real compound back to the template pose, which is the Bose output. And then it does an energy minimization, trying to give you a chemically feasible pose. So this is good, but I mean, this kind of gives us a concern because, if your template is good, meaning the Bose output is good, then this shall work fine. If your template is bad, you have some stereochemistry issue in the core of your protein, then we fear that this will give you a ligand pose which is highly strained. So we are also kind of trying the open-eye hybrid method as well, where it tries to generate some low-energy conformers and then try to rigid dock these conformations into your template. So this will avoid the issue where you can have a pose which is highly strained. It gives you another issue. So if your target pose is not in the initial conformers, for example here, where the ring is not in the right position, then you're not getting the good pose out. So we try to run ABFE examining different strategies where the crystal structure gives you like a 0.6 IMSE. And this is just the Bose output. And since Bose gets so many ligands wrong, I mean, it has the wrong chemistry. So you got a big IMSE. And when we use posit to dock it, our result is comparable, if not better than the crystal structure. And then the hybrid is pretty bad. It's illustrated here. If you get the wrong pose, you get the wrong binding free energy out. Cool. So another issue that we have with co-folding model is that you have clashes. And it is bad because your simulation will just blow up. So traditionally we have to handle this kind of stereo clash with homology modeling. You have your crystal structure, or in this case Bose model, as your reference structure, and you try to build a new sequence based on your reference structure. And in this case, we use ProMod3. So yeah, ProMod3 does do its job where to remove the clash, but it gives you some other issues as well, which is illustrated here. So Bose-1 kind of understands the protein-ligand interaction, so it will try to place the side chain in a way which benefits the protein-ligand interaction. The ProMod3 doesn't really understand the protein-ligand interaction, so it moves this arginine away. And as a result, if you use ProMod3 to solve your clash, you are worsening the ABFE performance. Obviously, you can't live with clash, so what are we going to do? So, co-folding model will give you a different model every time you run it. So you just brute force it, So for us, we run 10 models. And some of them will fail, and we just take the one which runs going forward. And we use the open-eye spruce trying to kind of do this clash detection. So in this case, we did a mini benchmark where we take all the compound in the OpenFF benchmark, and we take the strongest ligand out of each set, and we cross-dock them to the rest of the protein. And we try to see, okay, how many ligands, so the y-axis is how many ligands will give us at least X amount of successful models. So, it seems to vary target by target, but if you run 10 models, for all these 15 targets, you will get at least two successful models out for 100% of the ligands. So we are going forward with generating 10 models. So, okay, so this is kind of an internal target where we try to test this pipeline on. And, we got a long sequence. This is kind of almost 100, this is 100 residues. And the both one tells us that this region have a very low confidence. So, this is concerning. And if you check the protein ligand interactions, you can sort of see that the Bose-1 model is hallucinating about some interactions between the ligand and this low confidence region. Then we dig out a homolog of the target and we take the crystal structure and we check, okay, are these protein ligand interactions real? And they are not. So what are we going to do? Well, we are just going to remove the bad part. So just cut out the first 100 residues. So it seems that this is a good approach. And by cutting out this first 100 residues, you are also improving the overall confidence across the rest of the sequence. And it seems that for the region where Bose-1 is predicting high confidence, cutting off the first 100 residues is not really affecting the protein ligand interaction at all. And we are kind of capturing the crystal interactions as well, despite that it is a homolog. Cool. So there are other benefits of cutting off the low confidence region as well. So as I previously explained, we generate 10 models and then pick the successful model out of these 10 models. So if these 10 models are very different from each other, then we need to have an extra step to pick which model to choose. So in this case, when we are having the full sequence, we did a PCA on all the C alpha and the pocket, and we try to see, how close these models are between each other. And we cluster them by 3 clusters, and we try to measure the RMSD of each model to the cluster center. So if we have the full sequence, all the models are very different. This is kind of consistent with what you would expect. If you have a low confidence region and you ask both to make their guess, then every time it makes a guess, it will be a different one. And honestly, the difference is quite staggering. 3 nanometer in RMSD is pretty bad. But when you truncate out the bad part, it is much better. So there are, if you remove the first 100 amino acid sequence and all your region is high confidence, the models are all pretty close to each other. So you can just take a random model and expect it to be representative of all the 10 models. Cool. So, biology is always important. And in this case, we have a crystal structure where we kind of know the ground truth and the correct binding pose. So this green one is our target. And it is critical for this target to function in the presence of another big protein. And in the crystal structure, we observe that the ligand kind of binds in this folded pose. So if you are trying to do this kind of prediction, a blind prediction where you just try to predict the binding free energy between the ligand and the target, then you would generate your Bose model without the binding partner. And in this case, the Bose-1 will do a pretty bad prediction where it tries to predict the binding pose to be an extended binding pose instead of a folded one. And since, if you extend the ligand, the normal binding pocket will not accommodate it. It tries to change the binding pocket as well. Obviously, this is bad, and you can only recover the good binding pose and the structure if you include the binding partner in your Bose prediction. So here is some data with regard to this internal target, where we pick 10 ligands which we have crystal structure, and we try to compare the Bose model with the crystal structure. The red one is the full C alpha, and the C alpha of the pocket, the heavy atom of the pocket and the pose. So, you can sort of see that if you don't have the binding partner, every metric is bad. The protein is bad, the binding pocket is bad, the pose is bad. But with the binding partner, you kind of recover everything. Everything is now close to the crystal structure. And we compute ABFE as well, where the 0 is okay, so this is delta G, the crystal ABFE result. And 0 means that we are perfectly predicting the crystal ABFE. And the blue one is the ABFE with target alone. Orange one is the target with the binding partner. And we can sort of see that if you include the binding partner, the ABFE result will be much closer to the crystal structure ABFE compared to without it. So, well, this is a piece of knowledge which is good to have, but it is quite tricky to do this in a completely blind challenge because, it will pass through your pipeline fine, but you will get for ABFE result because you are not including the critical biology here. Cool. So yeah, this is the ABFE pipeline that we are having in our production, where you have the Boltzmann prediction, where you have the ligand small string, and you have the protein sequence. You predict the Boltz model, and then you try to solve all the crap by these two steps, where you generate multiple models to pick a steric mesh-free structure, and then you use the open hypothesis to reduct the pose. So you're recovering the correct ligand. And then you feed it into the ABFE pipeline. So yeah, so this is kind of a pipeline. So this is kind of how we test our pipeline with public data. These are kind of, our old friend, the TIC2, CDK2, JUNK1, and P38 in the OpenIF benchmark set. So we compare the, starting from the crystal pose versus starting from the Boltz. And the crystal, which is the orange one, it is always good. You got good result as usual. And for the Boltz output, then it is obviously worse than the crystal structure, but they are not too bad as well. From the beginning of my PhD, then we are kind of already thinking, how do you do ABFE without a structure? And at that time, we are kind of using homology models. We are getting zero correlation, and our RMSE is proportional to the dynamic range. So I'm very happy that even though that it is worse than the crystal structure, we are kind of roughly in the 1 kcal range. And in production, if we have a RMSE lower than 1 log unit, then it is considered as useful. And particularly in our case, since we are using it in the target deconvolution problem, and we are trying to, the result will be a binary classifier where it binds or not. So this kind of accuracy is kind of good enough for us. Cool. So yeah, it is a kind of shame where we can't really show any internal data, but I think the public data has already kind of shown that this pipeline is, well, it's a good first step, and it's kind of almost production ready. We show that we use Boltzmann to generate the initial structure and use ABFE to run the binding free energy prediction, and this allows us to get the use of free energy to the kind of early stages, and without the need of crystal structure. And the way that we do it is that we use the Boltzmann, we use the posit docking to correct the ligand chemistry, and we generate multiple models to correct for the hash, and remove the low confidence region to give you a good overall structure. And you need to get some omics people trying to tell you what are the binding partners which you should include in your model. There are obviously other issues as well with the current pipeline. So the Boltzmann cannot deal with cofactors. And recently there is this Boltzmann model which claims to solve all the issues which I have just described, and I have tested it. So it does not really fix the ligand chemistry. If you have some aromaticity problem before, you are still having it with Boltzmann X. And for the bond order, it is still getting the bond order wrong. It does fix the stereochemistry issue, but it fixes it in a very bad way, where it twists the ligand into an unnatural conformation such that it narrowly pass the stereochemistry test. So this is still something which the team needs to work on, and we need to validate this on a lot more situations, trying to figure out what are the things which needs to be improved. Right. So yeah, we show that by using co-folding model and ABFE, we can have a pipeline which allows you to get the binding free energy out just from the ligand small string and the protein sequence. And this will enable us to run the free energy calculations in the other stages. And I would like to thank the team for the work. And we have some people in the audience as well. So if you want to do some well, networking, then they are here. Cool. So that's all. And thank you very much for your listening.
Perfect. We have time for one or two questions.
Yeah. Okay, yeah. So I will start with the sequence part. So okay, so this 100 residues is a big sequence, so it can do a lot of things. And in this case, for this target, we have a kind of well, a very solvent exposed binding pocket, and both ones seems to have the tendency trying to make the protein into a globular shape. So if it sees a pocket and it has some residues which it needs to place it, it will try to place it in the pocket, which gives us a problem. Here it's kind of it interacts with the ligand, and since it is kind of in the binding pocket, it kind of affects the confidence of other residues in the binding pocket as well. So this is our hypothesis for the truncation. With regard to the binding partner, and the ligand obviously it prefers to be in the extended conformation compared to the folded conformation. So you have an energy penalty here, and I guess for both the energy penalty for extending the binding pocket to accommodate the ligand is better than in this conformation. But when you include the binding partner, if you try to extend the binding pocket, it will include a bigger penalty because you have to move this whole binding partner away. And as a result, it makes more sense to fold the ligand into a relatively high string manner than moving this binding pocket back and push this whole binding partner away. So this is our hypothesis. Yes. So okay, we have run our pipeline in the hit ID stage, which is we have a couple of hits against a number of proteins. So I mean, I share your concern that there will be a hit, there will be hit in accuracy. For our purposes, it's kind of identifying whether hit or not. So the drop in accuracy is not a too big a concern if our goal is to predict if it's fine or not. And we haven't really tested this approach in the hit to lead, and we need to test it more in this case. But I mean, as for hit to lead, then we kind of have more information in the protein, so there could be better approach than doing a blind prediction with both.
We are on time, so let's thank William again.